All right, Chem AP Aces, are you ready? We've got another Chapter 4 lab for you. This one's a Redox lab, okay? And it's going to involve titration, which we'll show you in a minute, but first you need a little bit of background information. So, what we're doing is we're going to react hydrogen peroxide and potassium permanganate. All right, so we're going to have a permanganate solution with a known concentration, 0.150. That's going to be in the burette. It's got a really nice deep purple color. And we're going to use that to titrate a hydrogen peroxide solution. And later on, we'll tell you what question it is you're trying to determine. Okay? And you need to know this maybe, in acidic solution, permanganate ions change to Mn+2 ions, and hydrogen peroxide molecules change to oxygen molecules. You're going to need that information. You're going to have to try to create a net ionic equation for yourself so you can do the stoichiometry in the particular drug.
Will we have to balance the net ionic equation too?
I would think you need a balanced net ionic equation. Did I not say that, Mr. Moore? Probably not. Or don't balance it. It's fine.
Doesn't matter.
Doesn't it? Yeah,
Okay.
whatever. Yeah.
So at our lab station.
Yep, we're at our lab station. We're going to get ready to titrate here. As we mentioned earlier, the permanganate is in the burette. It's got a really nice, beautiful,
Wow,
deep
what a
purple
great
color.
Looks like grape juice.
It does. But it doesn't taste like grape juice.
Don't think so?
No. Concentration, as we mentioned earlier, is 0.150. We know the concentration of the permanganate. Here is our unknown hydrogen peroxide solution. We're calling it sample B. Okay? Now, last time we had to add phenolphthalein, you recall, as an indicator, so we can mark the stoichiometric point. Permanganate's nice because it's its own indicator. It's this deep purple color now, but at the end of the reaction, it'll convert to Mn+2, which is colorless. And so you'll see that as we're titrating, you'll see the purple hit disappear because there's an excess of peroxide. But when we hit that end point, it's going to be a nice light purple color, and it'll tell us when to stop titrating. So here's the graduated cylinder I'm using. I don't know if you need my hand to... It's marked off in 10th milliliter
Yeah,
increments.
we see the graduations are 1/10 of a milliliter.
Yep. So I'm measuring out 10.00 milliliters as closely as I can. One more bit. Okay. I'll dump that in the flask. Now, as you know, these aqueous redox reactions tend to occur either in acidic or basic solution. This one happens in an acidic solution, so we have to acidify it. So Mr. Moore made up some 6 molar sulfuric acid, and we're going to squirt in a couple nice healthy dropperfuls.
So you're not measuring the sulfuric acid?
Nope, we just have to make sure that we have a good excess of hydrogen ions to be present. If we didn't put that in, the reaction wouldn't happen. And it's really the hydrogen ions that count here. The sulfate ion is just a spectator. I would forget about it when trying to do the net ion. So here we go. We should be ready to titrate. The burette is at 0.00. We ran a fast trial earlier, so we have a ballpark idea of how much permanganate is going to be required.
So we'll just plan on 2 good endpoint trials.
Yeah. Okay, and you can see that purple disappearing.
Oh, that's so cool.
It is cool. Now you'll notice
What
there's
else do
something
we
else
see?
going on. Yeah, something else going on there.
Add some where you don't shake it so we can see it.
Sorry. Yeah.
See what's happening there? Other than the color change. See the bubbling going on? Is that bubbling happening just because we're shaking two liquids together? Let's look back at the chemical equation.
Yeah.
It's always a good idea when you have your chemical equation and you see the reaction, make sure that what you're observing is consistent with what the equation says.
Okay, I'm trying to not overshoot this, so I'm going carefully. Spirit is very touchy today, so I'm afraid to open it up more.
I think we're getting close.
It took a long time for that drop to disappear. Let's see if I can get one more drop. Come on, baby.
Okay. Ooh, I think you got it.
There it is.
Okay. Good endpoint.
Permanganate
Okay,
is
I
so
need to
deep
start
in
this
color,
over.
it's hard to, well, you really can't see all the way through the burette, so you just have to do the best you can to read that volume.
Okay, so that is the final volume for trial. We'll call that trial 2 because trial 1 was a fast and sloppy one. And then there'll be the initial volume for trial 3. Manganese, like a lot of transition metals, is cool because different oxidation numbers of it will give you different colors. Manganese, when it's in permanganate, is this beautiful purple color, but when it's Mn+2, it has no color. That's why as soon as it hits the peroxide, it goes clear.
Okay. Same drill, we have measured out our 10 milliliters. Make sure it's well acidified. And here we go.
Come on. Ooh.
I think that's it.
Got it. Sometimes the iPad camera
Yeah.
chooses something else to make as its focal point. Oh, okay, there we go. Yep, do the best you can with that volume.
Yep.
Okay, so 2 good trials.
Yep.
Sample B.
And you will hear later what you're actually going to try to calculate about the peroxide solution.